With day 67 here, we're going to look at two different types of sums: midpoint Riemann sums, that's what the R is for, Riemann, midpoint Riemann sums, and trapezoidal sums. I'm also going to show you how to do these quickly, how to do our different sums quickly from a table. Okay, so I asked you today, or yesterday in the video, and today in class, what might be some other ways to approximate integrals that might be a little bit more accurate than a left sum or a right sum. We saw today that the more rectangles we add, right, the more number of subdivisions we add, the more accurate it gets. But without doing that, midpoint Riemann sums and trapezoidal sums are good ways to get a little bit more accurate of an approximation. So let me just show you, I'm going to show you what these pictures look like, and then we're going to do all four sums from data tables. So take a look here. I'm just going to draw a sketch. Okay, here I have some function, f of x, and I'm looking at this on the interval from a to b. So what I'm going to look at here is what a midpoint Riemann sum looks like first. So first here, let's go ahead and write this midpoint Riemann sum. I'm going to do a midpoint Riemann sum with, let's say, n equals 4 subdivisions. Okay? So I'm just going to chop this up into 4 pieces, right? If we knew what b and a were, we could do b minus a over n to figure out how wide each subdivision is. But since a and b are just letters, I'll just sketch 4 equal subdivisions in here. I'm going to say equal subdivisions. So I'm going to sketch those in here. Is that a different color? There we go. Okay. So there are my 4 subdivisions, my 4 bases of rectangles. Right now they're not rectangles, okay? But we can see here, since this function is increasing, if I did a left Riemann sum, I'm going to end up with definitely an under approximation. I'm going to miss a lot of area. If I did a right Riemann sum, I'm going to get a lot of area covered that's above the curve that I don't want. So a left Riemann sum here is going to be too small. A right Riemann sum here is going to be too big. But a midpoint Riemann sum is very interesting in how it works because it can be a lot more accurate. It's very difficult to tell if it's going to be an over or under approximation, a midpoint Riemann sum, but it gives us a good idea of what's happening. So here's how this works. Instead of using the left point to make the rectangle for a left Riemann sum, or the right point to make the rectangle, like a right-hand Riemann sum, I'm going to use the point directly in the middle. So directly in the middle of these 2 pieces here, I'm going to make a dot in the middle in terms of x. Okay? And that's where I'm going to make my rectangle. So it's going to look kind of cool. It's going to look like this. Okay. Now, hopefully you can see right away the advantage to a midpoint Riemann sum. Because if you notice, I'm going to overcount that part right there. I'm overcounting a little bit here, but I'm undercounting a little bit here. And hopefully I'm kind of balancing those out so I get a much more accurate reading. Now, it's not going to balance out perfectly, but it gives me a little bit more accurate of a count. The problem is I don't know if I'm going to be too high or too low. Okay? So I'm going to go ahead and show you what the rest of these midpoints look like. So you can see in each of my subdivisions, I overcounted a little bit and I undercounted a little bit. This leads to a much more accurate answer again. So that's what a midpoint Riemann sum looks like. Kind of cool. We just use the point right in between the two. Okay, so let's take a look at a trapezoidal sum. Okay, so let's do a trapezoidal sum here. With n equals 4 equal subdivisions. Okay. I'm going to start this problem the exact same way I started left Riemann sums, right Riemann sums, and midpoint Riemann sums by putting my 4 subdivisions in there. So that one here, here, go as best I can right in the middle, and cut both of those in half. Okay. So now instead of using rectangles, right, left, right, midpoint, they all used rectangles. Now what I'm going to use is I'm going to turn each subdivision into a trapezoid. Well, hopefully you remember from your geometry days that trapezoids have one pair of parallel sides, right? So all I'm going to do is I'm going to connect each subdivision top to the next subdivision top. So it's going to look like this. And do that for each one. Now all I have to do is find the area of those 4 trapezoids. As you can tell by looking at this picture here, this is going to be a pretty darn accurate guess for the area under the curve. Now, if I drew this correctly, I should be overcounting just a hair. If you notice, those line segments count just a little bit of space above the curve. I'll just go ahead and shade here for you guys to see it. Now what I want to talk about is when do we have over approximations versus under approximations? Well, for left and right Riemann sums, it depended on whether or not the function was increasing or decreasing. Increasing or decreasing makes no difference for trapezoids. What makes the difference on trapezoids is whether our function is concave up or concave down. Okay? And a way to think about that if we just sketch something that's concave up, if I connect this with a trapezoid, I'm going to overcount, right? But if the function was concave down, and I connected it with a trapezoid, I'm going to get undercount. Okay? So, if f double prime is greater than 0, if we're concave up, our trapezoidal sum is overestimate. If f double prime is less than 0, my trapezoidal sum is an underestimate. Make sure you have that in your notes and make sure you memorize it. Now, for me to memorize it, I would always just draw a little sketch. Okay? Sketch something concave down and show that a trapezoid is too small of a guess. Sketch something concave up and you'll see that the trapezoid is too big of a guess. The only thing that makes trapezoids a little bit annoying is the area of a trapezoid is not quite as easy as calculating the area of a rectangle. Okay? So for the area of a trapezoid, right? So let's just look at this region here. Let's say it has a width of B. I already used B. Let's say it has a width of C. Okay? That's supposed to be a C. And the problem is it has two different H's. Let's call this H1. Let's call this H2. The area of this is base times the average of the heights. So it's base times height 1 plus height 2 over 2. Okay? All right, so if this was a height of 3 and this was a height of 5, and let's say the base was a length of 2, I would find this area by doing 2 times the average of 3 and 5. Well, the average of 3 and 5 is 4. 4 times 2 is 8. Okay. Okay. Let's take a look now at a table and see if we can figure out how to do. I had you guys make tables on your homework today because eventually what's going to be provided to you, the most common way that you have to do Riemann sums on the AP exam is from a table. So let's take a look at this table. Go ahead and pause the video right now and copy that table into your notes so you're not copying and trying to listen at the same time. Okay, so I'm going to do an integral estimation with all 4 different ways that we know. Okay? So first, I want to estimate the integral from 2 to 14 of f of x dx using a left Riemann sum with n equals 4 equal subdivisions. Okay, a couple of things about this table that are really important to know. Take a look at the spacing of the x values. 2 to 5 to 8 to 11 to 14. Are those equally spaced? The answer is yes. Each one is increasing by 3. That's really important to note. Some tables you get will be equally spaced like that. If they do that, they're going to ask for equal subdivisions. But sometimes they give you tables that aren't equally spaced out, and they'll just say, using the subdivisions provided in the table. Okay? So, I want 4 equal subdivisions. The first thing I want to do is figure out how wide are my subdivisions supposed to be. Well, my width is going to be b minus a over n. Well, b in this case is 14, a is 2, and n is 4. 14 minus 2 is 12. 12 divided by 4 equals 3. So the subdivision should all be a width of 3. Well, that's nice and convenient, right? Because that's how my x values change. They change by 3. So here's what I like to do to my table. My first subdivision is going to be from 2 to 5. Right? My second subdivision is going to be from 5 to 8. My third is going to be from 8 to 11. And my fourth is going to be from 11 to 14. That gives me 4 subdivisions, each with a width of 3. Now, instead of sketching a graph here and spending all that time like we did today on our homework, we can do this really, really quickly. Okay? Here's how it works. So, here's what I'm going to say. Integral from 2 to 14 of f of x dx approximately equals, okay? It's going to be the area of all 4 of those rectangles. Now, an area of a rectangle is base times height. The question is, for each subdivision, I have 2 different heights that I can choose from. I have one on the left and one on the right. Well, since I'm doing a left Riemann sum, I want to use the height that is on the left. Okay? So here's the question. Here's how we do this. Our integral from 2 to 14 of f of x dx is going to approximately equal all of these rectangle areas. So what's the base of the first rectangle? Well, the base of the first rectangle stretches from 2 to 5. That's a base of 3. And in fact, I already calculated that in my width section, right? So I know the area of my first rectangle is 3. But again, since I'm doing a left Riemann sum, for this first subdivision, I want to use the height that is on the left. So I'm going to say 3 times negative 5. By the way, it's totally okay that that's a negative number. We just get a negative answer for that particular one, which is okay because integrals, that just means it's below the graph. And obviously that is going to be a negative number, no problem. So that's the first one. But I got to add up the 3 other rectangles as well. Right? And it's a Riemann sum. I'm adding these things up. Well, what's the width of the next rectangle? Well, it stretches from 5 to 8, which again is a base width of 3. In fact, all of my base widths are going to be 3. But if I give you an unequally spaced table, like you're going to see tomorrow, be very careful with that, because those will be changing. Those bases will be changing over and over. Okay? So, my next one is, the base of that rectangle is 3. And now again, I want to use the left number for my height, 3 times 1. Plus, my next subdivision is this one right here. Again, my base is 3, and I'm going to use the number on the left, 9. Okay, so I've got 1, 2, 3 subdivisions. I have one more to do. My last one, again, is a base of 3, and the height I'm going to use 12. Notice I never use the number 20, because on a left Riemann sum, we never use that far right height. This doesn't get used for a left Riemann sum. I'm going to add these things up. This is going to equal negative 15 plus 3 plus 27 plus 36. Okay, negative 15 plus 3 is negative 12. Negative 12 plus 27 is what? 15. $15 plus 36 is going to equal, what, 51? So my left Riemann sum ends up with an answer of 51. I'm doing that math pretty quick without a calculator, so hopefully all the math is right there. Okay? That's our left Riemann sum. Now I want to do a right Riemann sum. So I'm going to estimate the integral from 2 to 14 of f of x dx using a right Riemann sum. And again, I'm going to do with n equals 4 equal subdivisions, just to make this go fast. Well, calculating this then is going to be really easy, right? Since I just did it the other way. Make sure you have an approximately equal sign there. Well, all my bases are still 3, right? Because it's n equals 4. Okay? But instead of using negative 5, 1, 9, and 12, I'm going to end up using 1, 9, 12, and 20. So this is going to look like this. 3 times 1 plus, right? So now I'm using the right number for this first subdivision. Then I'm going to do 3 times 9, then 3 times 12, then 3 times 20. Okay? So I'm using all of those numbers. For each subdivision, I'm using the number on the right, 1, 9, 12, and 20. Now, one thing that can save you time, especially if this is on multiple choice and you need to get the simplified answer, notice how, since we have equal subdivisions, I can solve this a little bit faster without a calculator, and I probably should have done that in part 1, by factoring out a 3. Okay? I just factored out a 3 because there's a 3 in every single term, because the subdivisions were all equal. 1 plus 9 is 10, 10 plus 20 is 30, 30 plus 12 is 42, so this is just going to be 3 times 42. I don't know what that is off the top of my head. I get an answer of 126. Okay? There we go. There we have it. Okay. Now let's try. I want to estimate the integral from 2 to 14. Let me check. Of f of x dx. So again, I'm estimating the integral from 2 to 14 of f of x dx using a midpoint Riemann sum this time. Let's try that. With n equals 2 subdivisions. Okay, first thing I hope you notice is that I changed the subdivision numbers. In fact, I can't do a midpoint Riemann sum with n equals 4 subdivisions because I just don't have enough information in my table. Right? If I was doing a midpoint Riemann sum with 4 subdivisions, I'd have these same markings up here. Well, I don't know what f of 3.5 is. I don't know the y value for the middle of 2 and 5. Okay? So I'm switching the number of subdivisions so we can actually do this. Just be careful anytime you see a midpoint Riemann sum with a table, because it's oftentimes it's not just going to use the ones that they have given. You're going to have to stretch it a little bit farther. First off, let's calculate our new width. My new width is going to be 14 minus 2 over 2, and that's 12 divided by 2, which is 6. So I'm going to go back to my table here. I'm going to erase these subdivisions that I have. Okay, so my new subdivisions have to be a width of 6. So my My first subdivision is going to start at 2 and it's going to finish at 8 because that's a distance of 6 away. My next subdivision is going to pick up right from 8 and go to 14. Now this is convenient because now I actually have the midpoint, right? So my first subdivision has a width of 6. I would use -5 for a left Riemann sum. I would use 9 for a right Riemann sum, but I'm going to use 1. Right? I'm going to use 1 for my midpoint Riemann sum. In the next subdivision, I'm going to use 12 for my midpoint Riemann sum. So here's what I get doing a midpoint Riemann sum here. Integral 2 to 14 of f of x dx approximately equals. Note my new width, right? I'm not using 3 anymore, I'm using 6. My first rectangle has a base width of 6, and I'm going to multiply that by that midpoint number, which is 1, plus 6 times that midpoint of, what was it again, 12? Yeah, in this subdivision, 12 is my midpoint. 1 and 12 are my two midpoints. 6 times 12. Okay? There's only 2 subdivisions, so I should only have 2 things that I'm summing together here. Okay? And again, I can factor out, or I can just do piece by piece. Okay? Factoring out, I got 6 times 1 plus 12, which is the same as 6 times 13. 6 times 13 would be what? Well, let's figure it out. I get an answer of 78. Okay, so that is my midpoint Riemann sum with n equals 2 subdivisions. Last but not least, I'm going to do the integral from 2 to 14 of f of x dx. I'm going to estimate that by using a trapezoidal sum with, let's go back to n equals 4 equal subdivisions. So this is going to be just like the example in my left and right. So I'm going to try to do this quick so you can get this video over with. My subdivisions are going to go back to being a width of 3. There's 1, 2, 3, 4. Okay? But now here's where it gets interesting, right? I take that base length, but I have to multiply by the average of the 2 heights. So I'm not using -5 only or 1 only. I have to average those 2. Right? We average things in math by adding them together and dividing by 2. I'm going to average them to solve this problem. So here's how it looks. We're going to get lots of practice with this tomorrow. My first base is 3, but I have to multiply that by the average of the 2 y values. So I have to add them up and divide by 2. Plus, my next base is 3. My averages are going to be 1 and 9. Plus 3. My next average is going to be 9 and 12. Plus one more. Unfortunately, I couldn't fit it in the same line. My last one is going to be 3 times the average of the heights, which those ones are 12 and 20. Okay. Again, the nice thing is if this is on free response, I can just circle that. That's a fine answer. Tomorrow in class, I want you working on simplifying them. Let's take a look at what this would be. -5 plus 1 is -4. -4 divided by 2 is -2. So that times 3 is -6. Plus 1 plus 9 is 10. 10 divided by 2 is 5. 3 times 5 is 15. Okay? I'm just evaluating each piece here. plus 9 plus 12 is 21. 21 over 2 is 21 over 2 times 3 would be 63 over 2. Plus the average of 12 and 20 is 32. 32 divided by 2 is 16. 16 times 3 is 48. Okay. And simplifying that down, negative 6 plus 15 is 9. So we'll call that 18 over 2 plus 63 over 2 plus 96 over 2. I'm just changing these all to be over 2. 18 plus 63 plus 96. 6 and 3 is 9. 9 plus 8 is 17. 10, 17, 177. So my answer is 177 over 2. That's it for today. Kind of a long video, but it's going to be a good one to reference back to and take good notes on. See you guys tomorrow. 2 trains. Bye.